Banach fixed point theorem. This is a very famous theorem, and I think every mathematician has to know this theorem and what does it say. Okay, given some mapping on Rn, maybe R to R, function of one variable, and the result is a number, or R2 to R2, the input is a point in the plane and the output is also a point in the plane. And if this map has a special property, the special property, not every map has this special property, but if this special property, there is a constant less than 1, let's say 0.995 or 0.2, then if for all input arguments x, y, this is true. What does that say? Okay, there is a distance of the input arguments. Think for the moment that there is not a norm but an absolute value, then it's the distance of 2 points. And if the distance of these 2 points multiplied with a constant less than 1, then we get less of the distance the points, the input points have, then the output of the 2 input arguments, and then take the difference. So that's the distance of the mappings. If this distance is less than the original distance was, then we are in the situation that Banach fixed point theorem tells us something. Then what does it tell? It tells us then there is exactly one fixed point of f. What is a fixed point? A fixed point is a point where the image is the same as the input. We will see later some examples. And on top of that, we can find that fixed point by doing very easy thing. Iteratively input your argument, get an output, and take that as the input of f again, and then you get an output, then take that output to be the input, and then iterate that process, and then you converge. It's guaranteed to converge to this fixed point. Now we should try to make more sense of that. We talked about a norm. That's something you have an input argument and then you get a number which is more than 0, or it might be 0 if the input is 0. So what about a distance? If you take a difference, x minus y, think of these numbers that they are on one line. If that is x and that is y, what is measured by that? It's that distance. So it's a distance on the line of all real numbers. And now think of 2 points in the plane, if that is the first point and that is the second point. And then we can measure this distance. And what is the way we normally measure this distance? We take x minus y, and then we take the Euclidean norm, and then we get that distance. But instead of using the Euclidean norm, you can also use any norm. Then it's not this distance, but also some kind of a distance. So having that, this is measuring a distance. And what were the properties? There were 3 of them, V1, V2, and V3. What was the first property? A norm is a norm, in this case measuring a distance if and only if this should be a number which is at least 0. And the 0 is possible if and only if this is the 0 element, and in this case this means x is the same as y. Okay, this is V1. That means if the vectors, different points in the plane, then the norm must tell us a distance which is larger than 0. And if x is the same as y, then there is no distance, it's 0. And never, never, never we have a negative distance. Okay, what was V2? V2 means if that is the point x and that is the point y, then on that line, then this distance must be exactly 3 times the original distance. And what is V3 in the context of measuring distances? We need the following. If this is point X, this is point Y, and this is point Z, then the distance of X and Z is less or equal than the distance of X to Y plus the distance of Y to Z. And that means that going straight line from X to Z, it's less than going from X first to Y and then to Z. And if Y is on the same line, then we have an equal, but it's never shorter to go from here to here doing that bias. And for the Euclidean norm, all that is true. And using a different norm, not the Euclidean norm, we also measure distances, but in some kind of strange way. Okay, now we understand that concept here. We talk about distances. And as I said, the distance of the mappings is less than the distance of the input arguments. There must be a constant which is less than 1. And then for all pairs of input arguments, this inequality holds. The existence of that constant means that the mapping of 2 points leads to a less distance compared to the original distance. And you can prove that. This is the hint for the proof. The distance from a point to the fixed point, mapping these 2 points. For the fixed point you get the point himself, and so the mapping is closer to the fixed point, and so we will get convergence. Okay, so let's have 2 examples where we have such a C constant less than 1, and let's have an example where we have a C larger than 1. Let's have an example where n is 1. So we have a map like that. And now let's take 2 input arguments, whichever you want. Let's say this one and that one. And then this is the distance of the input arguments. And here, this is the distance of the output arguments. And here we have a larger value than we have here. So if that is f of x, then f of x minus f of y is larger than x minus y in this example. Okay, and let's have a second example. Here in that part it's kind of critical, so that was not a good example. Maybe we should continue like that. And now if we choose x and y, let's choose x and let's choose y. Then here we have a distance x minus y, and that is the distance of f of x minus f of y. It doesn't matter which order we have, because if you take the absolute value 2 minus 3 and 3 minus 2, this is always the same. So f here in this example is not contractive. In this example, f is contractive. Here, this one single pair shows that it's not contractive. Here, this single pair does not show that it's really contractive, because it must hold for every pair of x and y. We saw that for this specific set of x and y it was true, but it has to be true always. How can we see that this is contractive and that is not? We can see it from the derivative. If f is a map which you can differentiate, then you can see from the derivative. Here the derivative is less than 1 between 0 and 1. It can also be negative, but then between 0 and minus 1. So in total, the derivative has to be between minus 1 and 1, or better, between minus c and c. If the derivative is always in that interval, then C is the constant we need. And here in this example, we have derivatives less than 1, less than 0.5. And in this case, we have derivatives more than 1, and then it's not contractive. And that's what we have here. If we talk about a map R1 to R1, so R to R, then we are in the situation, what are the norms on the set of R? There's more or less only one single norm, and that is the absolute value norm. More or less means mathematically you can multiply the norm by some factor 5 and then it's still a norm. Let's forget that. Let's say for f there is only one single norm, and this is the absolute value norm. And then this property, what is that? Then this can be replaced by the derivative has to be an absolute value, has to be less or equal to a constant which is less than 1. And if that is true, then it's guaranteed there is one single fixed point, and we can find this single fixed point by starting at some arbitrary point, starting point, and then iterating that process. So let's have two examples to better understand that. Let's start with f of x is a half times cosine of x. And then we are asking, is there a fixed point and how can we find it if there is one? So we are looking for the fixed point of f, which is a map on R. And that means we are looking for a solution of the equation cosine x times a half is x. And let's have a picture here. What is the graph of a half times cosine x? If this is 1 and this is minus 1, then here we have a half. And if this is 1, 2, 3, then here we have a pi, and here we have pi halved. And now we have this graph. And here on that side also like that, and up and down again and again. This is f of x, and now we can look for f of where is f of x equal to x, and that means where do we have this intersection point. Here at that point we have f of x is equal to x. And where does it lie? Here in this sketch it's more or less near to a half. So let's examine that together with our computer. So let's plot our function and let's plot our fixed point line, and let's run that code. And then we see the following. Here we have that single fixed point, and where is this fixed point? We can zoom in. It's in the vicinity of a half, as we saw in our paper. And if we zoom in, we see 0.4502. And indeed we can find that point with an arbitrarily chosen starting point. Let's start with x to be 0 and then iterate the process. Take the x as the input, and then you get an output which is 0.5 times cosine x, and that will be our next input argument. So let's iterate, and we come closer and closer to the fixed point, which we saw was 0.4502, and this looks like very good. Okay, now this digit is constant, and most likely this is the desired fixed point. What did we see? We used x0 to be 0, and then x1 was a half, and the iteration went that way. And 18 also. So this is the fixed point, and that means we found the solution of cosine x times a half is x. And why was it guaranteed that we are in that situation? Because the derivative is between -1/2 and +1/2. Why is that true? The derivative is -1/2 times sine x. X is in between of -1 and 1, so multiply with -1/2. So the derivative is between -1/2 and 1/2, and that means that the derivative absolute value is less or equal to 1/2, and 1/2 is a constant which is less than 1, and that means that the iteration will converge to one single fixed point which exists in that situation. So let's go back to the script. What I've written here is kind of restrictive. It can be formulated a little softer, and that's what is that remark about. Usually the Banach fixed point theorem is formulated not for the whole Rn to Rn, but instead you can replace Rn to Rn with a d, but it must be the same d here as here. And it has to be a complete metric space. What is that? For numbers, it's an interval with these brackets. If it's of that kind, then it's not a complete metric space. So for numbers, it's more or less that. And if n is 2, 3, 4, then it's more or less the equivalent, some interval of that form. And that means for R2, it's a rectangle here in the x1, x2 plane. Okay, have that in mind. And if we have a function operating on this subset in the way that the image of an input argument is also element in D, and if there is also this constant C with the properties above, then f is also of the form that there is exactly one fixed point, and we can find that fixed point starting the iteration with some point in D starting. Let's have an example for that. Let's examine the following example. F of x is 1.1 times cosine x, so 1 plus a tenth. So in this case, f prime is 1.1 times sine x, and the negative of that. And that means this time this derivative is not less than 1. But what can we do? If we have a look on the plot, I did that and I checked which interval we can use. Then I found, after some tries which were not successful, for the interval 0.6 to 1, then the following is true. We have f. What does that function look like? That form in 0.6 and 1 is in that part. And in that part we have the situation that f of 0.6 and f of 1 is the value for 0.6 is, no, it was not 0.6, but we have to use 0.5. Yes, now indeed we have the situation that f of 1 is 0.59 and the value for 0.5 is 0.9653, and in between we are in between. And let's examine the derivative. And this derivative is at most 0.9256, and this is less than 1. So we are in the following situation. This value was 0.9653, and this value was 0.5943, and so we have this interval, and let's use that notation. It's not really correct. Normally I should use brackets like that, and I have to swap these elements, and to avoid all that I write it that way. Okay, and we are in between. We are not in that situation that we have also values which are minus 1.1. No, we are always in between of these values because we are on that section. And f prime, we saw the prime value for 0.5 was minus 0.5274, and the prime value for 1 was minus 0.9256, and in between it's in between, so there is never a derivative minus 1.1 or 1.1, and so we are really in that situation. And so it's guaranteed that we have a fixed point, and we can find that fixed point by starting with some arbitrary point in that interval. Let's choose 0.6. Doesn't matter which one we choose. And then iterating this process, you can do that by yourself. What do? 1.1 times cosine 0.6, and then I get, and then take that as the input, 1.1 times cosine of that, and then you get. And iterating that process, it takes a long time. You can do that by yourself using MATLAB or Octave. Then after a long time, let's say after 37 steps, this has to do with what? The derivative. This is close to 1. The absolute value is close to 1. And so it takes a longer time. If the numbers were in between of 0.1 and 0.2, this convergence would be much faster. In this case, after a long time, you get these answers, and that means that this is the fixed point. Okay, let's check that here. 1.1, instead run that, and here we have the plot, and there is exactly one fixed point in this interval, and this fixed point is 0.7811. So let's go back to our script. So far we had examples only with n is equal to 1, and now we want to have an example where n is 2. We can still draw pictures, we could draw pictures, and we can easily imagine what's going on. And so let's have an example. Let's have the following example. F of x is 2, 5 plus some small numbers, which will imply that we will have contraction, and this x vector is also x1, x2. Okay, if we have that map, we can show that it's contractive. Why? What do we have to do? We have to have f x1, x2 minus f y1, y2. I want to write it that way. And what is that? This one is, and then minus, and then that, and then this cancels, and then with the law for matrix multiplication we can write that to be. And now measuring that distance, let's measure this time not with the Euclidean norm but with the maximum norm. Then we have, now using the, for matrices, the row sum norm, and for vectors the maximum norm, then we can apply what we have seen in the last video. They are consistent norms, and then we can write it that way. This is less or equal to that, and here this is the row sum norm. The row sum norm 0.4, 0.6, so we have 0.6 times that, and that's what we want. Now we know this is contractive because the mapping of the 2 points, the distance of that is less than at most 0.6 times the distance of the input arguments, and now we know this map is a contractive map, and that means there will be some fixed point. And we can do that, we can find that fixed point. We can start with every point whichever we want. So let's start with 0, 0. If we do so, what is x1? If we apply 0, 0, it's a 0, so x1 is 2, 5. And then x2 is now this time 2, 5 here, so it's 1.7, so 3.7, and here in that line minus 0.4 plus 2, it's 1.6, 6.6. And now taking that to be here and then multiply and add that, then you will get. And instead of doing that by hand, we can use a computer and he will tell us. And after a very long time, I will show you. Then we have a long time, okay. Then we have 4.5 exactly. It seems to be exactly 4.5 and 6.8333, and this seems to be 7 minus 1 divided by 6. That's the assumption when I see these values. But now I want to show you electronically here this iteration. So this time we start with 0, 0, and then we iterate. X is the update to 5 plus, and we get 2, 5, 3.7, 6.6, and so on, and iterating that. Oh, it's much faster than I remembered. Convergence is very fast. And that is not really surprising because we had a constant 0.6, and that means convergence can't be really slow. Okay, it's really very fast in that case. And now to close this video, I have a really funny example, a real mathematics example. And this has to do with maps, with real maps. Let's open that map. And what do we see? We see Göppingen. That's the place where I am sitting right in that moment. I am sitting at the university complex, and this complex is here. This black building. I am sitting in this black building. This map is on my desk. And now I can say, okay, we are here. And the question I want to ask is there any point of the map being exactly not 1 millimeter or 1 micrometer or whatever, but exactly at the position, the point on the map is exactly at the position the map is right now in this moment? And this is true. Why? We can view the world to be R2 or part of R2. And this real world is mapped to points on that map. Okay? The real world is mapped to points on that map. And the image of 2 points, the original distance, in this case is 3.7 kilometers. But the distance on the map here is 7 or 8 centimeters. So the distance on the map is less than the distance in original. And having this 1 to 50,000, that means that the shrinking factor is 1 divided by 50,000. The distance on the map is less or equal, and in this case it's always equal to exactly 1 divided by 50,000. And we are measuring distances by the Euclidean norm, and so applying Banach fixed point theory means that there is exactly one fixed point, so there is one point in reality which is mapped exactly to the point the map is here. And I can turn the map a little, and now it's not still anymore the same point, but now it's some different point which is exactly at the position. The point on the map is exactly at the position where the map tells us. For practical purpose, it's always that building which is exactly where we are. Being an engineer, I think you say, okay, what is he talking about? But being a mathematician, there is exactly one point on that map lying exactly at the position where the original point in the real world is. And that's quite funny. And this application is not an engineer application, but I think it's an application which is easy to remember. But what is going wrong if you put that map on your desk, being in New York, sitting in New York maybe, then we don't have anymore the situation f d to d. Then this is no more true. This map should be placed on some desk which is in some city of this map. Then you have really D to D. Then you have one point in reality being mapped to a point on the map exactly at the position. Okay, that was our video about Banach, about a very fundamental theorem in mathematics. And as I said, every mathematician must know Banach. No mathematician is allowed to forget that. And in the next video, we will use the Banach theorem to prove the convergence of Gauss-Seidel, or better, the Jacobi iteration. That's what we will do in the next video, and we will need this Banach theorem.